We're still building the theory for relationship theory. We're still building it, so please bear with us if we don't have any new lectures. So today is just a filler lecture on Footnote for Femboy theory. Now, I'm sorry if my voice isn't that heard well because I'm wearing a very thick mask. So bear with me on this one. Okay. So today we're going to be talking about F infinity, or F infinity, and this is just the Femboy counterpart of the C infinity set. C infinity, or I guess this is F infinity. All the same thing, just notational variation. Now let's say just for the purpose of this video, let's build the theory from the ground up. Now, in regular algebra, we've always worked with R, the real numbers, which encompasses or contains the integers, the rationals, the naturals. These three. And of course, we're talking about R with the standard Euclidean topology, wherein we're able to measure distances. So you have a distance function norm that maps R onto itself, or R2, or R cross R. Take two inputs, yield one output. And we're in this dot product of xy is equal to the square root of x squared plus y squared. Or rather, the distance between x and y. So x minus y, the absolute value of that. So it allows this, that Euclidean metric allows this. So I suppose, of course, since we're able to do all of this on R, it's a metrizable space. And we're also working with the ring R. So we're working with this structure here. R plus and dot. Excuse me. So R with the plus and minus operation. Now recall that a ring implies that this structure R equipped with plus is a recall that R equipped with the plus operation is a group, and R equipped with the product is a commutative monoid. So that here, this here, is a group, or this one's a commutative monoid. Recall that from the definition of a ring. So we're working with the ring and the standard Euclidean metric. Now I don't add, now division is not part, or we don't equip R with division because division is already defined as multiplying by the multiplicative inverse. So this operation is not included. Because so take an input, say A and B is equal to just A multiplied by the inverse of B. If we're going to divide A and B, and then BA equals B times the inverse of A. Yeah. So, okay. Let's do that with Femboys now. So instead of thinking of every point well, whether two-dimensional point or one-dimensional point, instead we're going to think of them as of course people, but of course we still kind of treat them as points so that we're able to, we have some notion of distance between any point. So instead now, we're going to replace this with our standard universal set of all femboys, which is F. So F. Equipped with this and this. It's still closed because adding two femboys or multiplying two femboys yields a femboy still. Okay? And it's still part of the set, so this is still closed and it's still a valid structure, and this still forms a group and this still forms a commutative monoid. Same thing. Okay. And of course, F is with the standard Euclidean metric or topology. Standard Euclidean or metric or topology. Okay. So now think of a curve. So let's think curves. Okay. Let's think curves now. So think of a curve gamma that maps the closed interval 0, 1 onto F. Think of this curve. It could be thought of as something like this, such that this is F of 0. I mean gamma of 0, sorry. And then this is gamma of 1. It's a curve. Everywhere differentiable. And this, actually let's start in the R case. So the one we usually think of. So when we make graphs, this is the more abstract version of it, the higher level version of it. So you notice that from gamma 0 onto gamma 1, gamma of 1, this is everywhere differentiable. So we can take derivatives at every point. We can make a tangent vector here, we can make a tangent vector here. In fact, this is a local maximum. And then we can take a tangent vector here, and notice that this is a local minimum. So we can take tangent vector. There are no breaks here. There are no like that. No, it's all smooth. So that's good. Now, this curve gamma, if thought as a function of x, is an element. All right, element, not subset. Is an element, or rather just gamma, not gamma of x, because gamma of x is the image, not really necessarily the function itself. So gamma is an element of what we call C infinity. Because it is smooth everywhere. Because C infinity is a very broad set. In fact, it is just the set of all smooth functions. All smooth curves. That's why it's called C, after all. I think we can use C, not really math BBC, because that's notation for the complex numbers with an infinite tuple, which kind of doesn't make sense. Okay, so since we can differentiate gamma at any point on its curve, of course, or any point in its visual representation, then it is part of C infinity. Something like, let's say, let's make a piecewise curve, let's say alpha that maps 0 to 1 onto R. And then this is its visual representation. And then this is alpha of 1, and this is alpha of 0. And then there's a break here. This alpha now is not an element of C infinity. In fact, we're not only saying, because C infinity has two contexts here. C infinity can either be a property of curves, or it can be a set where curves exist in, or can be a part of, or element of. So we can say also that not only is gamma part of C infinity, or is an element of C infinity, but gamma itself is a C infinity curve. Okay? Or it is C infinity, which means it is smooth everywhere. Now we can take derivatives at any point that we want to. But here we can't take a derivative at this point here because it makes an abrupt jump or finite jump from one image to another image. So we can't take a derivative there. But here, however, we can. But do take note that what I'm saying is a bit of a misnomer. When I'm saying that we cannot take a derivative here, it's sort of it's a bit ambiguous in the world of abstract algebra because we can take derivatives here. However, we can only take left and right derivatives. In this case, we can only take a right derivative and a left derivative, but not a total derivative. As you come to know that, like here. Okay. Okay. So alpha is not an element of C infinity, or it is not C infinity, and gamma is a part of C infinity, or it is C infinity. So it's smooth. Now let's apply this in our context. Okay. So instead of mapping 0 to the closed interval 0 to 1 onto R, let's say now that it maps onto F. Okay. And then this is still the same visual representation. Remains the same, but instead of points we have various femboys. And they're all lined up in such a way, like this. So it's more of a spatial thing now, rather than just an abstract way of thinking about them. So now we think of each of these images as a corresponding y value. So let's say that I make the origin here. At this point x, the corresponding y position is this point here. And notice that it makes sense in the case of spatial, a spatial direction, because in real life we can walk in any direction we want. There is no undefined location on Earth, right? Or in the universe, there is no undefined location. I mean, you can say that a black hole is an undefined location because we can step in it, because we get turned to spaghetti, or anything that gets into it turns into spaghetti. But the point is, locally speaking, we can walk in any direction we want and get as close as we want to a certain point. Not infinitesimally, like how we take limits, but still we can get closer and closer to a certain thing, and we can still get there. Okay? Or to a certain spatial point in our three-dimensional space. So like in our three-dimensional space, you can walk up to any femboy here on this plane. And that's what makes the C infinity. Now if it's something like this, of course we can't really get to this point, can we? Because this is defined as 2 points. Right? So when we take its limit, it doesn't exist. The limit does not exist. That's another defining attribute of C infinity curves, or C infinity manifolds. You can generalize this into any n manifold, so long as that manifold is smooth manifolds. But this is classified, or C infinity is reserved mostly for 1 manifolds. So 1 manifolds elements. But when we start talking about curves though, or when we start talking about surfaces, it's a different story. Though we can still say that a certain manifold is C infinity if it is differentiable anywhere, especially if it's something like a differentiable manifold where you can perform a calculus on it. It would certainly help, and actually it makes a bit sense because by logic, a surface is just a bunch of infinitesimally put together 1 manifolds, right? and this definition would make sense for them, though it's mostly just used for one manifolds or curves, really. So smooth here, not smooth. So this is not C infinity. This is not C infinity. So yeah. So because our inputs here are femboys and not precisely one-dimensional points, one-dimensional numbers, we don't say just C infinity. Because C infinity is mostly smooth curves with real inputs, real number inputs, so inputs from R. But our inputs are actually from F, because you'll notice that a gamma of X is equal to Y, but notice that X and Y are not part of R, but rather X and Y are part of F. One input and one output are both elements of L, as you'll notice here, and of course in this output. Femboy's spatial femboy direction or location in the Y direction, and femboy spatial direction in the X direction. So, anyways, so our notation now for the set of all smooth femboy curves or F curves is FC infinity or F infinity. This or this. Though I think I'd prefer using the MathCal version of F, because this math BBF is our denotation for an F manifold. So though it's still loosely related, because F infinity is a family of one manifolds, one F manifold at least. So this is loosely connected. Or if our F manifold here, or F manifold is a one manifold, it could be homeomorphic or homomorphic to one of the curves here, or some curves here, of course, unless our one manifold has a break. So yeah, so I guess that's really it. That's really all you need to know about curves in this context. So okay, so yeah, C infinity, F infinity. So if an F curve or femboy curve is F infinity if it is smooth at all points, that's a summary, I'm just making a summary. And it is an element of F infinity. So now gamma is just, it's not C infinity, there's rather F infinity. Alpha is C infinity. But I must note that the set F infinity is isomorphic, I'd say. It's sort of isomorphic to C infinity. That's a notable thing. These two are isomorphic sets. So let's write it down. C infinity, the set of all gamma that maps 0 to 1 onto R, such that vertical denoting such that not differentiable. Smooth. And then there is this here. F infinity. Same thing. Gamma map 0. 1 onto F such that gamma smooth. So there's your definition. So yeah, I guess that's it for this footnote. I highly suggest you guys check out the playlist for this course if you guys are a bit confused with the chronological order of these videos. Really check the playlist out. I'm going to be posting this, of course, in the playlist. in its right place, right after the F polynomials video, I think, or F curves. So, yeah, more abstract definition of a polynomial.